Yeah, good evening, everyone. Thank you for joining. Before anything else, let me tell about the speakers. So, today is our engineering silicon from the system intent to RTL to GDS. And here are our speakers. I am Sheikh Hassan Pasha, and I'm silicon design engineer from Ignytion IO. And here comes our founding mentor from Silicon Setu community. So, Hariharan Sheshadri, sir. So, he'll be telling us about the Silicon Setu and the OpenSoC project which they are working on. And next, our CTO of Ignytion IO, Samjit Mandal. Thank you for joining. He'll be explaining us about virtual prototyping today. And before anything else, two thank yous. We are joined by the team from Silicon Setu, and the whole second half of tonight runs on their silicon. So they're open source RISC-V SoC. So it will say I'll say more about them when we get there. And this session is supported by the Banyan Circuits community. Thank you for Ramesh sir and to build everyone to at Banyan Circuits for having us. Building a community where engineers actually turn up and learn together is harder than it looks. And it is the reason this session exists. So let us coming to the today's agenda. So let us coming to the today's agenda. Here is our plan today. So first, the map will look all the steps of the chip design one by one. So you learn what words mean. This helps you in interviews. And then we look at the decisions that happen early. So before you write any code, before you write any code. So after that, we compare digital and analog experiments. And then I show you the tool we use. And then we do two demos. In the first demo, we run a complete RISC-V computer that does not exist. Linux boots on it, and a custom AI accelerator that does the math for the neural network. So there is no real hardware in that demo one, which you are going to see. And then the next real RTL, we'll go a step down. We'll be simulating the Silicon Setu OpenSoC project, which is level 1. So we'll be taking entire logic, when entire their repo, and we'll be recreating that on our Crucible Workbench. And please ask questions in chat anytime. I'll answer as we go. And let us start with the word VLSI. So VLSI means very large scale integration. It means we put millions and billions of transistors on one small piece of silicon. So and all of them must work together correctly. So this is the hard part. So and look at the numbers on the left. Uh, Today the smallest parts on the chip are about 1 nanometer. That is very complex and small. And at that scale we are able to see a DNA clearly at that nanometer scale, and one chip can have billions of transistors. So after you send your design to the factory, you wait months to get the real silicon. The last step is important. You cannot fix a chip after it is made. If there is a mistake, then you should wait months and pay a lot of money. And coming to the every stage in order, so this is the map. If you remember only one thing or one artifact from this session, so you can consider this. So you remember this only one slide today. So the left side is called as front end. So it has specification, architecture, RTL design and RTL verification, synthesis and gate level simulation, and also the design for test, which have a separate role. And coming to the right side, we have the backend. So it is also called as PD, physical design flow. So it has a floor plan, placement and clock tree synthesis, routing, and sign off and fabrication, and also the post silicon validation. And coming to the front end versus back end. So and front end and back end, it is the full map. If the full map is too much, remember this simple difference. So the front end asks the question, is the logic correct? Is it behaviorally correct, if we can say? And what should chip do? And does my design do that? So these works feel like software. So you write code, you run it, and you fix bugs. So in the backend, ask different question. So the backend asks about, can we build it? Will it be fast enough? Now you think about physical things. Where does each part sit on the chip? How long is it? How long is the wire? And does the signal arrive in time? So the same design, two different types of work. So when people say I'm front-end designer, you consider that the person is going to work on the logic side of the chip. And when a person is saying back-end designer, then that person is working as physical things of the chip. And coming to the architecture specification, so now let us go step by step in the chip life cycle. So the specification is the first step. So here we write down the exactly what it must do. So where are its functions and what are its connections? How fast it must, and how much power can it use, and how big can it be? And coming, we call we consider parameters while writing the specification. So performance, power, and area. We call this as PPA, and you will hear this word many times today. And coming to the next stage, so here we are at the architectural design. So in this step, we decide the big structure of the chip at the very abstract level. We do this before writing any code. So it describes about how many blocks do we need, and how do they share memory, how do they talk to each other. So look at the picture over here. So there is a CPU, there is a memory, there is a digital signal processor, and here we also have IO ports. So in between, we do have an interconnect, and this connection is also a design decision. So this decides how much data can we move per clock cycle, or this decides the faster or performance of the chip. And we also ask, are our PPA, performance, power, and area targets possible, or at architectural design itself? We answer this with simple models and calculations, not with real silicon. And coming to the next part, before starting the RTL design, so actual logic will be developed in the RTL design. Before developing the RTL design, now we had to take a hard decision which plays a vital role. So now two decisions that come between the architecture and RTL. This is the first one. So every function must go somewhere. You can build it as real hardware on the chip, or you can run that on a CPU as a software. So look at the picture, one function, and there are two possible ways. One is hardware and one is software. And hardware, when you consider the hardware, so when you consider your specific function should work on hardware, it can do many things at the same time. So hardware uses less energy, but you cannot change it after the chip is made. Once the silicon is manufactured or fabricated, so the logic cannot be changed. But when it comes to the software, it improves the flexibility or range of access. So for example, software can be changed later. So even if the chip is sold, they are very, and this is the way our software updates in our devices will come. And more hardware means more chip area, more risk, and more time. So most real chips use both. Where you draw the line is very important. And coming to the alternative of logic development, so we can say alternative. So here the second early decision, do you write RTL code yourself? So this is the other way. It is called as HLS. So HLS is abbreviated as high level synthesis. So you write the design in C++ or System C, then a tool creates the RTL code for you. And look at the picture at the right side. So your C code goes into the HLS tool and Verilog comes out of it. After that, it follows the normal path, which we have discussed earlier. The verification part, synthesis part, and then DFT, and then the PD flow. And here comes the actual main part, the RTL design. So here we write the design. RTL means register transfer level. RTL design, now we write the design. So RTL means register transfer level. You can describe the behavior of the chip clock cycle by clock cycle. So you use the hardware language, which is Verilog and VHDL. Look at the code on the right side. You are not drawing the gates. You are describing what happened on every clock edge. So the tools will make the gates later. And coming to the verification part, so the biggest step in the whole project, verification means checking your RTL does exactly what specification says. So we have written some set of rules that should be followed, like PPA or functionality checks, so that whichever we have written in the specification, so that should be verified over here. You write a text bench, the text bench sends input to your design. So then you run the simulation, and then you'll be verifying the waveform, and you'll be doing the coverage part. So where it will be telling what are what and all the functionalities and how much part of code is covered actually. And the RTL design and verification. So these both processes runs in a loop. So for example, RTL initially designs the logic and gives it to the verification team. So verification team connects it through an interface. So they'll be checking the functionality of the RTL. and then they'll be, if they find any bug, if they find out any possible error, so they'll be reverting back to the RTL design, and RTL design team will work on again logic development, and this loop goes on till the specification is exactly repeated over here. The specification checks have met or not, and then after this after we confirming that the design is following the spec 100%, then we'll be going to the next step called as synthesis. So synthesis is where your code becomes the hardware. So the tool takes three things. One is RTL, and which you have written just now, and then the library of standard cells. And the standard cells are the basic cells from which you can construct a sock. And then you have your constraints. So the constraints file which we are going to give is the SDC file, so which is abbreviated as silicon design constraints. Look at the picture on your right. Your always block, which we have written just before, has converted into an AND gate, an OR gate, and the D flip-flop. They are connected together, and the clock drives the flip-flop. So this way, the synthesis process converts the real code into the synthesizable logic, or a circuit, if you can say. And after that, we'll be getting the gate level simulation. So now the artifact which will be generated from synthesis will be the gate level netlist. So we'll be getting the gate level netlist and the area and timing report with the numbers. So after that, we'll be having the netlist and we simulate it again. And you may ask why. So why simulation again? So because we have already simulated the entire code in the verification part. So here is your answer. So we already tested the RTL. So the reason is synthesis is the translation step, and translation can create small problems. So reset problems or unknown values spreading through the design. So these problems can appear only here. So it is the same circuit as the last slide, but as we add SDF delays, and SDF gives the real timing numbers for each gate. So as we have propagation delays for each gate, so we'll be getting the delays in this simulation. And next come the design for test part. So this step is about the factory. So it is not about your design. So that means what I mean it's about the factory is, so when a wafer comes back from the factory, some chips will be bad. So you cannot say which is bad or which is good. So if you can say which is healthy chip or which is not bad chip. So getting errors is normal, but how do you find that bad ones? So you cannot test a billion transistors by hand. So we add extra logic. Look at the picture. So we take 4 flip-flops and they are already in the design. We connect them in the chain. The output of one goes into the output of next. So this is called as scan chain. Now you push a test pattern into the chain. So runs one clock cycle, then read result it is out. So if the result is wrong, then the chip is bad. So the process used in this scan chain patterns is ATPG, which is abbreviated as automatic test pattern generation. And this will be tested after the silicon got manufactured. And next comes the with this the logic design part is completed, and we'll be going to the physical design part. So here we are in the backend. So from now everything is from here everything is physical. Floor planning means deciding the size and the shape of the chip. Where do big blocks go, like SRAM and PLL, and other large parts. So where do the input comes and output pins go? So then we add the power grid. So the orange lines over here are the power grid, and it brings electricity to every transistor on the chip. And the gray boxes which you are seeing here are the IO modules, so which are staying outside the sock. And so in this floor planning, you will be deciding where these SRAM and PLL should sit, large modules, if we can say. So for example, here we have SRAM and PLL, so which is phase lock loop. So if these both modules are communicating frequently, and if these modules are placed far long, then the distance is equal to delay. So as more the distance, the delay of the device will be increased, and the PPA will be traded off. So in the floor planning, we'll decide how long the module should sit, and next comes the placement. So now in the placement, now every small cell gets a position in proper rows. So the goal is simple. Cells that are connected should be close each to together. So for example, as discussed in the floor planning, so same cells which are communicating frequently will be sitting nearer. Why? Because of the one important rule, distance is delay, as we discussed, and a long wire can take more time. And if two connected cells are far apart, your chip will be slow. So the tool also manages the congestion, and too many wires in small area makes routing impossible later. So to make routing simpler in front, so we'll be taking this. We'll be doing this placement step, and after this, we'll be checking the timing parameters. So that flow is called as clock tree synthesis. So here the clock is like heartbeat of the chip, and it must reach every flip flop, right? So the problem here is that one wire cannot drive clock to billions of transistors, so that the signal becomes too weak and it arrives on different times. So we build a tree of buffers. So look at the picture over here. So the clock starts at the top and it splits again and again, and it finally it reaches the flip flop. So we build the tree of buffers, and we want to reduce the skew now. So the skew is the timing difference between two flip flops. So for example, this flip flop got clock edge or triggering edge at 1 nanosecond, and this got at 2 nanosecond, which are intended to get at the same time. Then the behavior will change. So only the clock tree synthesis also plays a vital role. And the proof that this stages work, that you will be getting a skew report with the values inside your budget. And next comes the routing part. Here, everything. So whichever the logic and part, whichever done till now, everything will be converted to the real metal wires. So routing has two parts. One is global routing plans, has the general path, and then detailed routing draws the actual wires on specific metal wires, and it follows the factory rules. So the factory rules are nothing but PDK rules, which we'll be discussing in the future next slides. So modern chips have more than 10 metal layers. So this picture is simple. Vertical wires are one layer, and horizontal wires are another layer, and the squares that you see are vias. Vias are the connects with the one layer to another layer. And this is where every connection in your code becomes a real metal. So in this process, so what is a proof that this stage is worked? 100% routed, no shorts, no open connections, and clean reports. And this after this we'll be getting the sign off and fabrication stage. This is the last check before we spend a lot of money on the fabrication part. So there are four important checks that you need to do before sending any sort of chip, either it is SoC or IP, any sort of chip before fabricating. So in that, first thing will be static timing analysis, which is STA. So this checks the timing and the skew and the other parameters whichever we have discussed just before. And then comes the DRC file, DRC rule checks. So this is abbreviated as design rule checks. So that checks whether the layout follows the factory rules or not. So factory rules, I meant by factory rules are given in the format of PDK files. So that using that PDK files in the synthesis process, will be generating the synthesis. So that rules should be followed. And coming to the LVS part, it is abbreviated as layout versus schematic. That check the layout matches your design or not. And coming to the extraction, so the extraction checks the real resistance and capacitance of the wires. So as a SoC will be having many current carrying metal wires placed near with a nanometer at a nanometer scale. So that wires may generate some resistance and capacitance also. So that will be studied over here and checked over here. So when all these four artifacts are clean, so we create the GDSI file in this sign off and fabrication stage, and you can see it in the picture. So the design.gds, this is the file we are going to send to the factory. And after the silicon gets manufactured, after some months, the real chip comes back, the real silicon comes back. So now we put them on a board and test them. Does the real chip work like the design said? Does it reach the speed and power targets as discussed in the specification, or any other factors that are changing when we have simulated it over RTL verification and over here? So we'll be comparing the both. So we started, and also notice something, we started with the simulation and now we check against the simulation. So in this we are going to check every rule check we have written in the simulation, we'll be checking it on the real wafer. So the proof that this stage is worked and the proof that your silicon is ready to operate, uh, that means real chips that can meet the targets which are specified in the specification. So that will be considered as healthy chips, which we have discussed before. And also here we'll be using the DFT logic for knowing whether the chip is healthy or bad. And till every digital chip is analog inside. So everything until now which we have spoke is a digital flow, but that is only the half story. So the digital design only uses the discrete signals, which are zero and ones, clocks and states and clocks. You write the specification and then RTL, then text bench, and then you'll be verifying the waveforms, and then you'll be doing the synthesis, and then PD flow, place and route, and GDS. This digital flow is having two automatic tools. So this is why engineer can handle millions of gate these days. And when it comes to the analog design uses the real voltages, gain, bias, frequency, and the values are also are continuous, not zero and one like the digital design. So the flow looks similar, specification and the schematic and the spice simulation, ANSYS layout, and then GDS. But there are few tools, few automatic tools, and the automatic layout is done mostly by hand, and so only by most experienced engineers, as it is manual. So now here is a point that surprises many people. So every digital chip is analog inside, and after adding the analog part, so we have started with the specification, we have written the logic, and we have synthesized it, we have verified it, and we generated added the DFT, and we have generated the every route till routing and place and route. So then comes the analog part. So in the analog part, you're going to add all analog modules like PLLs and everything. So after that, we are going to generate the GDS file. So this is the artifact which we are going to give to the fabrication or factory. So GDS is abbreviated as Graphic Data System 2. So which goes to the factory. So there are three things that must happen to tell how does this GDSI becomes a real chip. So the first thing, you're design using the real factory process. So the factory process which I meant is the PDK file. So the PDK rules should be followed. The factory gives you the rules and the models. And secondly, you finish the sign off and with clean results in all the four fields. Three fields here and one more extraction. So all the results should be clean. And the third step is you send it to the factory. So the open PDKs you should know here are Sky 130 and Global Foundries 180 and IHP 13G2. These are real processes, and you can design any design on these technology nodes today also using the open source tools. And coming to the platform we use, which is called as Crucible Workbench by Ignytion IO. So before running anything, let me explain the tool we use. So the Crucible Workbench is a platform from Ignition for chip development. The command called as igni will be used many times today. So you'll be seeing this command many times today. And here are the four simple ideas. An environment is a named group of tools. So the environment will be holding the named group of tools. So here you'll be doing entire RTL to GDS flow in one window. You no need to navigate to other window. You no need to worry about the installations. The installations will be taken care by Ignition, and you rest the design part is yours. And then comes the workspace. A workspace is your project connected to the environment, and the tools are installed and run by the platform, not by you. And the most important one is the reproducibility. So you can lock your workspace, you can share it. So then the person who is working in your team will be getting the same exact result. So let me tell the hard part while working with the manual installation, because I wanted to be honest about something. Most people who stop learning chip design do not stop because of their ideas are hard. They stop during installation. Those they spend full week on installation one EDA tool, and they get the error and they give up. So look at the left side. So you search for each tool separately, and you fight with versions and file paths. Finally, something works, but only on your computer. Nothing is reproducible. And after 6 months, if you cannot repeat your own result. So the right side is what we do today. So one environment defined once. So the tools installed by the platform. Every command is run through the Igni, and the workspace lock and sync will be able to help you with the reproducibility. So which I'm going to show you in the next demo. So one the line at the bottom is the real lesson. So it is true for any tool you use. The environment is the part of experiment. So if you cannot run it again, you cannot trust it. So let's end theory now. Let's run and see how the demo goes and how both experiments will look like. So let me explain the agenda of experiments or simulations which we are going to do. So there are two demos. So they sit at two different levels. That's a whole different point. So demo one is a virtual prototype. So that means a model of complete chip running on the software on my laptop. So we will boot the Linux on it. We'll add custom AI accelerator that has been never built, and we'll run the neural network on it. So which is completely software. There is no hardware code or logic written over there. And coming to the demo two, that goes one level down to real hardware code. We take the Silicon Setu level 1 SoC, a real RISC-V design from the IIIT DM Chennai team, and we build its hardware, check the code, and simulate the actual hardware, and open the waveform and verify it over there. And from now, I'll hand over to Samijit, and Samijit will be sharing about the virtual prototype.
Yeah, sure. Thanks, Hassan. Hopefully I'm audible.
Yeah, you're audible.
Okay, yeah, sure. Yeah, so first of all, thank you everyone for joining our session. And I am your host now, Somijit Mandal, and I work for Ignytion IO. So till now, Hassan has tried to give you an overview of how digital circuits designing as well as implementation works. And this is the part where I will show you how you can leverage the power of software or simulations and do some explorations and do some research and playing around with various kinds of socks and peripherals and cores and all that. So firstly, I would like to ask all of you, how many of you have heard of RISC-V cores or even tried any of the RISC-V cores? Can you just react to the chat? And yeah, I can see some hands. So yeah, very nice. So RISC-V, I'll quickly tell you what that is. It is an open instruction set architecture specification. So yeah, that's great. That's great. So a lot of you have used here. I see even Walter White has used RISC-V, so that's great. So RISC-V is an open instruction set architecture, and what it enables developers like you and me is to play with the architecture, define your own instructions, add your own instructions to it, and basically build your own core, own CPU core. So once you have built your own CPU cores, what you can next do is you can take it in a SoC. So a SoC is a system on chip where we have all the components that we require to achieve a systems engineering. So you want to solve some real world problem, okay? So that's why you are developing a chip. So an example I can give you is let's say some very basic some basic thing you want to achieve, like you want to implement a doorbell camera video conferencing system, right? So someone comes to your door and you want to talk to them before you allow them elementary. Or you can think of some, let's say, tea machine, like the ones you see in your offices. So these are small gadgets, small daily electronic items, and all of these have these microcontroller units or SoCs inside of them. And that is how, by building such small electronics and small products, you gradually scale yourself up, you learn the required things, and then you are able to build more complex circuitry and complex IPs, such as, CPU cores, complex cores, GPUs, and a lot of things can be built like that. Yeah. So here, my attempt here is to show you how you can, do such kind of research and such kind of development of peripherals as well as processor cores or whole SoCs, without having to go and buy, let's say, a processor core or any of the peripherals from the market, right? So you don't have to buy any of the boards. You don't require an FPGA board. So simply, if you just have access to a laptop or a computer system, which has, let's say, 4 to 5 gigabytes of RAM, that would be the minimum. You should be able to simulate the behavior of these kind of SoCs, right? So that is my goal here. So let me introduce quickly all of you to the system here. So here you see the VexRiscv CPU. That is the main core that we are using here. It's a RV32 IMA. We also have a MMU, so memory management unit, and it's written in Spinal HDL. So Spinal HDL is a framework. I think it's in Scala. So what you can do is you can define the behavior of peripherals and cores using Spinal HDL, and it then translates it into Verilog or any of your conventional HDL languages, and then you can carry on rest of the chip design flow. So in the center, you will see the wishbone interconnect. So wishbone is a type of bus. So like you must have heard of some industrial buses like, let's say, AXI Lite, or AHB, APB. So these are all the ones that I just mentioned are all buses coming from ARM. So apart from that, Wishbone is, again, I think it's an open source bus. So it's like a bus. Apart from that, you can see below we have ROM, SRAM, main RAM, one UART peripheral. And the most interesting thing here is the Ignytion Axle, right? So this is our custom peripheral accelerator model. It's very simple, but it is able to run some kind of AI and machine learning workloads on top of it. So I'll just show you. Another highlight here is on the right hand side. You can see we have the guest OS, which is Linux 5.0.14. So we have also we are not only running this simulation, but we are also running a Linux on top of it. And I'll also show you some of the binaries that we can run on top of it. Yeah. So Hassan, can you get the next slide? Okay, so I think this is better if I show you directly the demo, and then we'll come back to the slide. So I think I'll start sharing now. Hassan, can you give me the permission so I can share?
Yeah, yeah.
Yeah, so the demo that I'm going to show you right now, and I'll also briefly show you the repository and where I have worked on these things. So I'll show you the source files and how I have built this, and the whole thing runs on the Crucible platform, and how I am able to, run this and manage my workspace and projects using the Igni CLI, yeah, which is the CLI of the Crucible platform. So yeah, I still don't have the screen share permission, Hassan.
Can you recheck Sanjit? I have shared.
No, not yet.
Now.
Can you check in the host permissions? Yeah, yeah, I have it now. I have it. Yeah. So please let me know once my screen is visible to everyone. So
Yes,
I'll
it is.
simply, yeah, okay, great. I'll simply pull up my terminal here, and I'm starting with the first command like Hassan showed you in one of the slides, which is igni init. And this banner will show you that you are now ready to work with the igni CLI. And I'll just navigate to my already existing directory, and I'll start the script there. So I'll show you what it is. Yeah. Yeah, let me actually first run it. So here I have a simple script called run demo.sh. So I'll just launch it. And this is how Igni is programmable. So just like you write any of the shell scripts, you can embed Igni commands inside your shell scripts, and you can automate your workflows, your existing workflows for your projects or any fresh new projects. You can automate it like this. So here it just starts the Crucible, then it searches for Renode. So I already have the tool installed, and you can see that quickly a UART terminal came up. And those of you who have booted Linux previously would be familiar with this kind of message sequence. So this is what Linux boot sequence shows you. And as you can see, I have a TTY terminal here. Yeah, so I'll simply write root here, and now I am accessing this terminal. So I think I will start again from Igni init. So
Yeah.
I was showing the RISC-V accelerator demo here. And so I just did Igni init, and let me just navigate to my existing workspace directory. So this is my existing workspace directory. And firstly, let me try to run the demo here. So I have created a simple shell script here. So I'll just launch that one. Yeah, so you will see a terminal come up here, a UART terminal, and this terminal looks different from the one that I have on my system. So why is that? Let me actually show you. So I'll just first log in into this machine using root, and if I do uname -a, so you will see here that the machine it's showing is the architecture it's showing is the RISC-V 32, and the Linux build root is the 5.0.14. Whereas on my machine, if I do uname a, here you can see that I am running another different Linux machine, and the architecture is also x86-64. So this terminal clearly is not from this machine, and it is coming from within the simulation. Yeah. So the SoC that I had shown you, this is the simulation for that SoC, and that CPU is running in that simulation, and then it is booting up the Linux binary. So once it has successfully booted up the Linux binary, then we can say that yes, our simulation is running fine. And here I have also logged in into the TTY, and let me show you the binaries in this. So I have a few binaries that I have cross-compiled from my host machine for the RISC-V 32 architecture, and then inserted or injected them into this Renode simulation. And let me actually run the mnist classify binary to directly show you what it does. So this is a digit classification workload, and the goal is to be able to classify handwritten digits here. So as you can see, the digits are here 8, 7, 6, 0 to 9, and it is able to predict what the digit was. Yeah. So now I will show you how this was made, how this training was done, and how I was able to create a binary all from my host machine and run this simulation such that this demo that you just saw, this is able to run and able to classify the handwritten digits. Yeah. So for that I will just kill the terminal for now, and let me open the directory to quickly give you a overview of what is happening. So on the left hand side, you will see here I have arranged my source files, and Renode requires two kinds of files. So first one is the .repl file, which you see here. So using the .repl file, what you can do is you can assign peripherals and where they exist in the bus. So where the processor will be able to see them. So addresses you can give it like this, and you can also give their size. So how much memory map they will consume, you can give for all the peripherals that you require on your SoC. So a few examples here. What Renode allows you to do is you can pick up n number of CPUs, n number of peripherals, and you can mix and match and play with them. And you can place something on your on some address and then change it and see the effect, right? So this is what REPL file allows you to do. And this is especially very useful for embedded developers. So embedded developers who want to develop let's say firmware or some kind of embedded C code to run on their chip. If they do not have access to the chip, or it is a brand new product that you are working on, then what you can do is you can utilize the platform and socks and the boards on the Renode platform, and you can write this kind of REPL script here, and you will be able to simulate it and then try out your binary or C file on top of it. Yeah. So let me go into the SRC file here to see you what binaries we have here. So yeah, okay, I'm on the right branch. So here you will see the main file here is ignition accel.py. So this is the definition of my accelerator IP. And as you can see, the register map is very simple here. So I have a control register, a status register, a config register, which will help me choose the mode in which my IP is running. So three kinds of operations are supported in this IP, like dot product, element wise add, and ReLU. And then these two are the input vectors where I will be giving the actual values, and then the output will be seen here, and then a few other vectors are here. Okay, so this is a very simple peripheral, and the idea is to yet it is able to run the digit classifier. So the idea is to start very simple and just use a very high level language like Python, which is very comfortable to use, and then you can define the behavior like this. So Renode has this Python peripheral class, and inside there you can refer to their documentation, and there you can basically set what happens when a read or write operation is performed on your IP. Yeah. Then the other file of importance is the mnist classify.c. So this is the classifier. As you can see, it has the same addresses, and I have functions for register, read, write, and so on for resetting, etc. And first I'm taking the dot products. So these are for that. And then some helper functions. But below the main thing is here you will see the main file, main function. Yeah, so this is the main function where we actually, this is the one that runs on the VexRiscv CPU. And one point here I would like to highlight is the training is done on my host machine. So training is done on my laptop, but inference is done using the accelerator IP. Yeah. So once you have trained, so here is my training script, train mnist.py. I have trained it using this, and it gives me this header file. So as you can see, this is a regenerated header file. So whenever you change some weights or biases or some kind of training thing you are changing, then you just need to run the train mnist, and this file will be generated. And what this file contains is the weights and biases for the layers in my neural net. So here you can see L1 weights and L1 biases, similarly L2 weights and L2 biases. And this is the final layer that gives the 0 to 9, this one. And as you can see, the weights are quantized to integer 8, but the biases are not. These are full 32-bit biases. So finally, what I do is I compile these two, the header and C file. These are changed into a binary. And let me show you the binary here. So once the binary is created, it will be named, I think, mnist classify, this one. What we do is we create a root file system, and using the cpio command, we inject this binary directly into the file system. That's why when I, let's say, run the demo, you will see the terminal come up, and inside the terminal I already have the binary there. So here is the mnist binary. I have some other binaries as well, which I
So Abhijit, can you
created to test.
maximize the screen? Yeah.
Yeah, okay. Yeah, is it visible now?
Yes, Abhijit. Yeah.
Yeah, okay. So what you can do with such kind of methodology is you can incrementally develop your IP. So for example, in this case, I started with a simple mnist classifier, which is the digit classifier. But now I know that yes, my design works for simple tasks, simple workload like that. So the next thinking is, can I update this? Can I update my design? Can I update my IP to do some image classification as well? And then accordingly, you start with an image manage workload and do the same kind of thing. So for example, here I have the CIFAR train and classify, just like the MNIST you see. I am currently, that is what I am working on. And actually, let me try to see if I can run that as well. So just like you work with your software products, software projects, you do the same, because ultimately the simulation is again a software. So that is what we get the advantage, how we get the advantage of virtual prototype is softwareization of your hardware designs and hardware work. Yeah. So I am able to run and see the behavior of all these things. I am able to write my C software or firmware that runs on top of real hardware without having to get my hands on the real hardware or board or SoC anywhere. Yeah, so once I am confident in this, I will be able to write my RTL better as well. I will be able to do any kind of future training better as well. And when I'm fully confident that yes, my IP looks good now, I will go ahead and do the rest of the thing. I will create a real IP out of it. Yeah. So this is how pre-RTL exploration or system level or functional prototyping helps you to quickly come up with ideas, and not just come up with ideas, you are able to also validate those ideas, run the things and see how the effect changes. Yeah. So for example, in this case, you can see it is still working, it is still showing the correct prediction, and I am able to see the images, but it is a bit slow. So this is the next thinking in the architectural direction, that okay, how can I optimize my design now? Do I need to change the core? Do I need to change the clock frequency? What can I do here? How do I do the UART, or do I need to change the bus architecture? So I will be able to play with it, and I will be able to come up with the solution and incrementally develop my IP here, or whole SoC or processor, whatever you are working with, you can develop here. So yeah, I hope this was the demo, and I hope it gave you some idea as to what virtual prototyping is, what functional modeling is, and how you can utilize such kind of methodologies to work on your local machine and find out what hardware changes you can do, or explore multiple hardware options by quickly prototyping using tools like Renode. So there are many other tools like this, not just Renode. Igni CLI has access to many such virtual prototyping tools, and you should be able to carry out your virtual prototyping work easily. Yeah, and we'll share the slides with you as well.
Sure, sure.
Yeah. So your screen is visible, Hassan.
Okay, okay. I have one more waiting. I'll be setting up there. Questions will be answered at the end of the session. So please draft. Whoever wants to question will be giving time for the questions. So yeah.
Yes, yes. In the meantime, you can of course drop in the chats, and I will take it from there.
Yeah, yeah.
Please continue, Hassan.
So as we discussed about this, so again now we are going to discuss about the Silicon Setu process. So from now, Silicon Setu set. So before we run the design, so I want you to know whose work you're about to look at. So the Silicon Setu is a initiative of Inadu CSP Foundation. The name means the bridge of silicon in Tamil. So this is exactly the job it does, a bridge between the college teachers, and what industry expects of you on day one. So this Silicon Setu is an initiative by IIIT DM Chennai. So the mentor sir, Hariharan sir has joined. So he is the mentor of that initiative. And here, what they do. So Silicon Setu, this is their program. In their words, it is worth a moment. So 2 semesters taught inside the college curriculum, run by people who build silicon for living. So verification leads, SoC architects, physical design engineers. So not a training vendor reselling slides. So look at the 4 pillars. The system thinking. So the students architect a SoC instead of writing the modules in isolation. So the hardware and software capstone. That is the FPGA validated with a GitHub portfolio. a recruiter can actually clone and run. And AI native curriculum, and the real pathway of the tape out and validation. So let us go in depth about this. So
for people to understand the concepts of how to integrate various cores and how SoC. These are very basic elements. It's like a beginner project, we can say. People can check out this from GitHub and start making changes. It's a sandbox mode. They can make few changes, understand how the entire environment, everything is available. They can check out the code, start making changes and build on top of it. And then we'll have the level 2, level 3, various levels are coming up. The complexity will increase, like a gaming kind of complexity will increase every level. Basic level is has a UART and GPIO and basic simple 4 KB RAM. So you can use this to understand how the SoC boards, how it achieves the peripherals and concepts like that. The beginner level chip, the next chip will be, we'll put the assignments very soon. We're working on level 2 SoC. We'll put a problem statement. People can, once they understand this, they can go to the next complexity, they can build their own SoCs. And it's objective.
and here I'll show the execution of this. So let me share my screen once again. So yeah, is VS Code visible, Somajit?
Yeah, Hassan, go ahead. It's visible.
Yeah. So as Crucible, Ignis CLI is the CLI platform. So here you can invoke the Crucible using Igni in it. So you can, as it is CLI platform, you can run it in any code editor also. So like Cursor and VS Code. So here I'm using the VS Code. So this is the repo which I got from the OpenSoC Silicon Setu team. So this is a basic initial look of the Igni CLI. So here, let us start working. So before start working, you can just give Igni -- help. So to get the help from anywhere. So for example, here you have Igni -- help. So just now you have used the Igni in it. So if you need status of what you're working, so the what are the environments which you have discussed just before, or so here it is saying the workspace and bounded environment is none. So let us create the environment first. So the environment is created right now. So let us create the workspace also. So I'm selecting the repo and then I'm giving the environment to bind. So here we have created the environment called demo new. So I'm giving that environment. So the workspace has been created and included it binded to the demo new. So hop into that and then start in installing the tools. Yeah, give me a second.
Yeah. Now it's
Yeah,
type
sorry for
something.
the interruption, guys.
Yeah. This is correct. Yeah, go ahead.
Uh, so yeah, so wherever you are trying to get some help, so you can just give -- help prepended by the command whichever you need help with. So for example, if it is workspace, so you can give igni workspace -- help. And if it is about environment, the same command can be repeated using environment keyword. So yeah, so now let me install the tools which is needed. Very later we need it for simulation. We are going to use the make file, so we'll be installing the make. and then GTK wave for waveform viewing. And we need compiler as we are building the firmware and deploying using the SoC. So we need the compiler to build the firmware. So we are using the compiler which is available right now. So the compiler is also installed. So let me start building it. So I can just give igni run make, and the make file is has been already defined over here.
Yes, this one. Yeah, go ahead.
Yeah, here let us build the firmware. So igni run make. So let us first clean the tools artifacts whichever have generated before. So now let me build the GPIO firmware, and then the firmware building process has been started. So here 120 the hex artifact has been generated, and then let us also do the UART thing. So the UART firmware is also generated, and 181 votes have been generated. So the firmware part has been done. So now let us enter into the Crucible. So here the actual workflow goes. So here I have added a parameter called as waves, so which will be generating the waveform file. So here the GPIO process has been running, and you can see that the simulation is running. So here you can see all pin checks has been tested, and you can also run the UART thing, UART also. So basically you are simulating a SoC over here. So on our platform. So here you can see that the UART has also been passed. So yeah, with this, the SoC simulation has been done. So give me a minute. Let me come back to the slides. Yeah. So the waveforms will be looking somewhat like this. So and coming to the demos which you have done two today. So let us compare the two demos. So because this is a lesson to make home. So they both are simulation, but answer the different questions. So the virtual type will be working entirely on the software, entirely on the system. So here we are doing the same RISC-V SoC on the system level. So we have booted the Linux on it, and we have software. I mean, we have done software simulation over here. And coming to the RTL simulation in the demo too. So we have ran a RISC-V SoC completely on the Crucible Workbench. And here is the simple advice. So boot the virtual prototype, just make it run, do not change anything. Linux come up and log in. So yeah, and the second thing which we have is the OpenSoC project from the Silicon Setu. So here we'll be providing the GitHub repo links of both. So here you can see the Silicon Setu Git repo, and also you can see the Ignytion IO's Git repo where you'll be getting the Crucible Workbench work. And we are listening at info at the rate of Ignytion IO. And if you need any help with the Silicon Setu and OpenSoC project, they are listening at support at the rate of Silicon Setu. And if anyone wants to try out the platform, and if anyone want to see hands-on of the Crucible Workbench on your own, so you'll be you can register over this QR code, and we'll be reaching you out. And we are building this tool with one motive. We need to bring the software developer flows into the VLSI ecosystem, and our motive is build silicon like software. And thank you for your time, and if any questions are there, we'll be answering.
So like just like for the machine learning and AI, whenever you have to work on any project, you go ahead and just launch Anaconda or Jupyter Notebook, and then you are basically set to go ahead and do your experiments. Similarly, we want to do the same thing with EDA, and we want to bring same kind of easiness and access to all the open source tools. So I think Hassan has showed you the catalog. We will be adding more and more tools as we go forward, and we want this Crucible Workbench to be a one-stop solution where you will not face any of the challenges to get any of the tools to work or change any versions or move between your workspaces. And we want to provide you a seamless experience for setting up and working with any of these tools. And as I said, going forward, we will also have Synopsys and Cadence tools in this as well. What is the support you provide if you register for the pilot test? For the pilot, uh, if you face any issues with running the Igni CLI, you just come back to us and we will address it. We'll see that it works for you, it works for your machine. So yeah, you can just reach out to us and we'll resolve your issues. Sir, can you basically summarize the use of this code in short words with important keywords to keep in mind, sir? Sure. In this session, we showed you how you can quickly and iteratively develop your own ideas for real world problems and transform them into circuits, transform them into SoCs, boards, etc. And how you can validate these kind of things without going to the market and actually buying the product. You can leverage the power of simulations, and you can simulate the behavior of the chip and find the answers to your questions. Okay, so can you share the QR again, please? Yeah, sure. The QR is here right in front. You can take a snip of it if you want. So this is where you will find the links. AI accelerator. Oh, sorry, I skipped a question. Sir, since I'm in my final year, I wanted to ask you for classes. I'm aiming for digital verification. I'm from Maharashtra. So, Jill, we do not have any classes or trainings that we do one-on-one. So please stay tuned with us. We regularly post on LinkedIn, as well as we have our YouTube channel as well. So we frequently post there, so you can go ahead and check that, and stay tuned with us to get access to newer projects or whatever we are doing. You will be able to keep it. Demo that I showed, Prasoon, the accelerator in that was written in Python. That is good for early prototyping, or when you want to just try out your idea like a rough work and see if it works or not. Then once you have some level of maturity in your IP, some design decisions that you feel comfortable about, of course you can go ahead and implement in Verilog or any of the higher level languages. For example, even you can use C and C++, or there is a framework called System C. So you can write your model or IP again in these things, and again simulate it using Renode or any other simulator. So that is also possible. Or VLSI Institute, that will help me name it. So there are some institutes, you can look it up, Jill. But yeah, as I said, for our material, you keep in touch with us using LinkedIn and our YouTube channel. Sir, can you discuss briefly about Crucible within a minute time? So yes, Crucible is our platform that we just demoed. Igni CLI is its CLI interface, so don't confuse, it's the same thing. And the goal is to provide you a single one-stop solution for hands-on VLSI work that you want to do in as your everyday day-to-day work. And we give you access to many tools, environments, and managed workspaces using which you should be able to easily carry out any of your experiments. Yeah. Can you say when
Yeah,
is the next session? I joined a bit late. Okay, I think we will have some sessions going forward early September. Whatever it is, we will be informing you quite early, and you will have a lot of time to join it. Yeah, so next time, don't worry. May I know up to which stage does this able to handle in the ASIC or FPGA flow? What is the achievement for PPA target with this only, not other any EDA? Okay, so good question. Let me answer that. As of today, what you can do with Crucible is largely on the front end, but we are also actively adding the tools for back end, analog as well as mixed signal along with FPGA. So as I said, we are planning for whole stack end to end. So all the way from our idea to GDS or bitstream, let's say in the FPGA side. So everything will be covered. But yes, as of today, we are mostly primarily heavily focused on the front end. But yeah, we are also working towards back end as well, which means physical design. Please share your presentation. Yes, we will share it. Sir, could you share YouTube channel? Hassan, can you bring the link? Sorry, can you drop the link to our YouTube channel here
yeah,
in
yeah,
the
yeah.
chat? Yeah. For self projects, can we use this platform?
One
Yes, of
second,
course.
Kamajit. I have one more question from other mate. So they said that can you basically summarize this use of Ignytion IO in short words with some
I
important key?
just yeah, I just did that, Hassan. I've taken
Okay,
that
okay, yeah,
question.
yeah, yeah. I'll
Yeah.
be sharing the Google link,
Yeah,
YouTube link over
YouTube,
here.
YouTube link. Yeah, yeah. For self projects, can we use this? Absolutely, Vignesh. That is the goal. Our goal is to enable developers like you and me, college students, hobbyists, any kind of researcher, those who want to dive deeper into personal projects or do some exploratory work. That is our whole goal. You should be able to use this platform for such experiments and project work as well. The Tickle script work in this tool. Yes, we have support for Tickle as well. Apart from it, Python.
Give us a
Bash.
second. Give us a second. Yeah.
Yeah. Then yeah, this I took question. I answered this already. Can you teach something about DFT? Okay, we can do some sessions in the future about DFT as well. Can you work upon the entire RTL to GDS flow in this tool? Yes, Tejas, you can do that in using Crucible. You can do entire RTL to GDS or even RTL to bitstream, which is the case of the FPGA flow. Front end in mean RTL simulation linting CDC RDC synthesis. So front end is the logic design part where you write the logic implementation for it and verify it whether your logic is sound or not, whether what you started with your initial assumption coming from the specifications, are they meeting or not. Once you are happy with your logic, once you are confident with your logic, you go ahead and implement or realize that logic into actual circuitry. So that whole second part is called the back end or physical design, where you take the logic which already works but now you have to actually create the chip. So the CDC and all these things, simulation linting, the linting comes before, but CDC and LVS, DRC, synthesis, these are part of the PD flow. When will be the next session? Very, very soon, Shahid. We will let you know. And Badrinath, I see you have asked a question. Can we use Ignition CLI in WSN and VBox? Yes, our goal is to use the Crucible platform on all the three platforms that we commonly use, Linux, Windows, as well as Mac. And that means WSL as well. So that is something that you will be receiving the access to in the future releases. So when you fill the we will share a form with you towards the end of this session where you can basically it's a pilot form. You can be one of the early adapters, and once you fill that form and once we are ready, we will also help you to run this locally. Is this ignition tool used in real world corp or only for? Yes, so it doesn't depend on the tool, Vijay. So you can bring in your own, let's say, hobby or academic or college level projects as well. And at the same time, you can bring in any real world projects as well. For example, the next part of the session, which will be shown to you by Mr. Hariharan sir, he will show you a real world project that we are currently running, the Silicon Setu OpenSoC. So that is a real project, and we are aiming at eventually going up to the level of tape out as well for that project. So it doesn't matter which kind of project you work with. You can work with any nature of project you can work with on Crucible. Is this tool open source? So good question. So I would say currently what this tool is only MVP ready. So we are actively developing it. The team at Ignition, we are building it. And as we get feedback from people like you, the community members, we try to improve it more and more and make it stable every day. So once we reach a particular stability and we are sure that yes, it should be helpful for everyone, we will go ahead and make it open source. But that is something that I cannot promise as of now, but in the future, that is definitely something we are working towards. Yes, yes. To join the program, or the early pilot that I just mentioned, Hassan here will be sharing till the very end of the presentation. You will have to stay for that. So just like YouTubers, I'm doing here. But yeah, you will get the access to that. The link to the pilot there, and it's a simple Google form. Just open it and fill it like you had filled for this kind of form for joining the session here. And yeah, using that, you will be added to the list of people one as well. So I mean, physical design engineers use this tool. So our goal is to go from idea all the way to GDS, Rajesh. So any stage, irrespective of front end or back end, logic design or physical design, every engineer will be able to work on the Crucible tool, and we don't distinguish anywhere. You can use all the tools from any of the cycles, any of the stages. What was your question, Vijay? Did I miss something? Let me scroll up. Like NVIDIA and Qualcomm use this instead of highly paid duopoly. So yes, NVIDIA, Qualcomm, and let's say the other EDA vendors and the companies that build these kind of tools, they also have their place in the market, and those tools are also required. So when you go into the cutting edge nanometer scene, where you let's say less than 10 nanometers and that kind of chips and highly advanced chips, when you want to deal with, then you have to go with their tools as well. But yes, you can also run those tools on Crucible as well. That is also something we are working towards. So today, as of today, you will only see the open source tools, because right now we can only add the open source tools. But going forward in the future, you will see Cadence, Synopsys, and Mentor Graphics tools in Crucible as well. Can you get full video on YouTube? Yes, yes, we will be posting the recordings for this session for on YouTube, so you should get the access.